All right, hey guys, it's Mrs. Walker here. I hope you had a wonderful Thanksgiving. I am going to try my very first video to review the study guide answer key for this Chapter 3 Waves test that is on Tuesday. I know you've been studying super hard for it. So I am going to go ahead and just go over this. And it is the same document that we went over on Friday together. So you can see right here where it says to complete this table with the mechanical waves. So we've got transverse and longitudinal are both mechanical waves. And the types include sound waves, water waves, and seismic waves. Those are our three types of mechanical waves. Then electromagnetic waves are going to include anything that falls on that electromagnetic spectrum. We've got radio waves, microwaves, infrared, visible light, which is our red, orange, yellow, green, blue, indigo, and violet, ultraviolet, X-ray, and gamma. Mechanical waves can go through solids, liquids, and gases. They have to have a medium, whereas electromagnetic waves can go through solid, liquids, and gases, but they can also travel through empty space or a vacuum. The parts of the mechanical wave, if it's a transverse wave, you've got your crests on the top and your troughs on the bottom. And if it's a longitudinal wave, you've got your compressions and your rarefactions, your close together part and your stretched out part. And then all electromagnetic waves are transverse. So like I had said over here, transverse waves have crests and troughs, which means that electromagnetic waves also have crests and troughs. All right, if I go down here to this picture that I have to label, I've got my rest position as number 7. The crest is 8. 9, the direction that the wave moves. And 10 is the direction the rope moves. So if the hand here is going up and down, that's the direction the rope is moving. Whereas the wave is going to start here, and it's going to go this way, which is why this is the direction the wave moves. We've got this perpendicular transverse wave. And then down here, number 11 is the trough. Then if I look at my longitudinal wave there, number 12, the wave and the little spring coil are both going to be going this way. Hand, hand, wave. The hand is going in and out. The wave is going in and out. They're parallel. So the wave and the coil for 12 and for 13. 14 is our rarefaction, that's our spread out part. And 15 is the compression, that's that close together part. (16) and 17, this is just like the worksheet that we did. I gave you the rest position, and then here in red, we've got our crests here at the top. The green is going to be our troughs down here. Okay. Our wavelengths that are noted in blue, it's going to be this crest to the next crest, or trough to the next trough down here. And then the amplitude is kind of hard to see, so I'm going to erase this. And the amplitude here is this yellow spot. That is rest to crest, or rest to trough, rest to trough, rest to crest. All right, down here we're going to do a little bit of math here. Oh, you know what? I forgot to mention that here we've got a high frequency and here we've got a low frequency. In the same given amount of time, there's a lot more crests and troughs going to pass each second with 16, the high frequency, than the low frequency. And you can see pretty obviously that the wavelength is much bigger in my low frequency. So a lower frequency is a greater wavelength, and a greater frequency is a lower wavelength. All right, let's get all that out of there for our eyes, and let's go down and do some math. So here we have this triangle with S, F, and W, and remember here that The speed and the velocity I use kind of synonymously. So you could use the S or a V. And here, this lambda is just wavelength. So if you want to do a W or a lambda, they both mean the same thing. So the formula for calculating speed, if I cover up my S, if I were to cover up my S up here, I'm left with an F and a W, and they're next to each other, so I multiply them. F times W. Speed is frequency times wavelength. For this next one, if I cover up my F, I have an S over a V. That fraction, or the S being over, S over W, that fraction with the speed over the wavelength denotes that I am dividing. So frequency is speed divided by wavelength. And then the formula for calculating the wavelength, I'm going to cover up my W, which is what I'm solving for. I have my S over my F, my speed over my frequency, which again would be division, speed divided by frequency. So if I wanted to actually put in real numbers instead of just variables, it says here that a sound wave has a frequency of 815 hertz. So they gave me the frequency and a wavelength of 3.1 meters. So they gave me a wavelength. They gave me a frequency. They gave me a wavelength. What is the speed? So I'm solving for speed. If I cover up my S up here, I have my F times my W. 815 hertz times 3.1 meters would give me a speed of 2,526.5 meters per second. The meters per second unit would be my speed, just like you drive a car like miles per hour or kilometers per hour. This is meters per second. Number 23, a sound wave is traveling at 459 meters a second. That's a speed. And a frequency of 27. So there's my frequency. So they want to know, what is the wavelength? If I cover up my W, I have S over F. So my speed of 459 divided by my frequency of 27 gives me 17 meters. And meters is my unit because they want to know the wavelength. And meters is my length. It's not my speed. It's not my frequency. It is the length of that wave. Okay, let's look at our short answer here. Number 24. State one way in which transverse waves differ from longitudinal waves. Well, their disturbance is perpendicular to the direction the wave travels. So like this picture up here at the top, the hand was going up and down, but the wave was going left and right. So that makes our T for transverse, or our perpendicular or 90-degree angle. Another thing that you could say is that transverse has crests and troughs. Longitudinal, the wave, the particle, and the medium, and the direction the wave travels are parallel. So they're going to be traveling the same direction, like little railroad tracks next to each other. Okay, like that slinky that I came around with. And the longitudinal waves have compressions and rarefactions. 25, define crest and trough and discuss how they relate to the wavelength of a wave. So this is a double-part question. Define these, and then how do they relate to wavelength? Well, crest is the highest point of the transverse wave, trough is the lowest point of the transverse wave, and the wavelength is the distance from one crest to the very next crest or one trough to the very next trough. 26, which wavelength has more energy? A wave that has a small amplitude or a wave that has a large amplitude, and why? Again, 2 question marks here, 2 parts of this question. We know that amplitude is the maximum distance that the wave moves from rest position, so that doesn't matter if it's transverse or longitudinal, but from the rest, and a larger amplitude means more energy. Smaller amplitude is less energy. Okay, 27. For waves moving at the same speed, which one has a greater frequency? Shorter wavelength or longer wavelength? If frequency is the number of wavelengths that pass every given second, if the frequency increases, more waves are coming every second, the wavelengths decrease. You can pack more waves in every second if you put them closer together. And then 28, it kind of piggybacks on 27. Describe the way that wave's frequency changes as its wavelength decreases. When the frequency goes up, the wavelength goes down. The waves are closer together. When there's less frequency, so less are coming by every second, it's because you spread it out. The wavelengths are longer, further apart. All right, I'm going to take a break right there, and I'm going to stop this video, and then I will start a new one.